Here I'm gonna talk about some embedded program I did for some microcontroller I received. So let's talk first about myself. So I work for Wobox. So basically I'm a C++ developer and I earn my money by basically consulting and contracting for customers working with C++ and mostly on the Qt framework because I've been working with the Qt framework before. For example, recently I was working actually as a contractor for the Qt company to work on the Qt for microcontroller project. So this is relevant for this talk in a way, but this different kind of microcontroller, and it's in C++. So, so the point is that on my free time, so I'm not paid yet to do some work, but on my free time I like to develop on Rust. So I've learned myself Rust because I think it's a cool language that has good potential as a C++ developer. I see some potential there. So I'm basically like in Rust I've been doing a few create like I can do like this, so it's old thing, but so I'm kind of maintaining the CPP crate, which allows to use C++ from Rust and QMeta object, and there is also this QMeta object crate I made that allow to use Qt and QML from Rust. So what's there in this program? Yeah, so I came to this meetup quite often already, and so today there is no quiz, unfortunately, but most of the time there is a quiz, and one of the prizes is this little thing, this little microcontroller. So I won the quiz. I don't know how it happens. And so I got this little thing. And I thought, I might as well do something with it. So there was a little explanation card with what it is. I lost the card, but I kind of took some notes. And so it's basically, it says it has an ARM processor, so it's a Cortex M4 with 100 megahertz, and it has 256 kilobytes of RAM. So this is less than the microcontroller I've been working for Qt because they had like a big screen. They had up to even 10 megabytes of RAM. So anyway, I thought, okay, let's try to do some Rust there. I got this thing at the Rust meetup. I'll do it. So there is a URL on the box. So I hope this will work. Yeah. So there was the. Yeah, so that's the little chip. So get a kit. No, I already have one. Let's get started. So okay, what do I need? An MXCHIP. Okay, done. Computer running one of those systems. Well, I have Arch Linux. I hope that's gonna be okay. Wait. And Azure subscription, yeah, I forgot to mention that those things are kind of sponsored by Microsoft. But okay, so well, we need to subscribe to Azure and then do something on the. I mean, that's kind of okay. I can plug the thing. I think there is even a cable here. So how is it? Okay, like this first, and then maybe here. Yeah, so it shows some stuff. Okay, good. But then, I mean, I don't really want to use the Azure account, and this is all online. So yeah, I thought, okay, no. How to let's search Google how to do Rust on embedded. Hello. Yeah. Well, okay. So there is apparently some book. So first link, how to do Rust on embedded, and so there basically here's some tutorial with some other microcontrollers. So the datasheet says I have a STM32F4 412, and they're using some kind of other ones, but okay, doesn't matter. So I basically need to have a Rust up, and I'm having a Cortex M4, so I'm just using this command. I mean, you need to increase the font. Yes, so if you have any questions or comments, just please speak. So yes, so that's the thing. We need to install Rust for the target. So because it's an ARM chip, so we need to have the standard library and everything compiled for this target. So we just Rust up to this target. I'm on Linux. I'm on Arch Linux, so I'm gonna install this. So we need basically GDB for ARM, and we need OpenOCD, which is basically to connect it connects to some debugger here in the thing. We need to set some UDEV rules. We just have to read this tutorial there, but then let's get started. Check if this is working, so we can let's see if I have it there. So we can increase the font. So I don't have so here I have a different one. So thankfully this is kind of auto-completing. So it kind of connects, and so we can check that we're connected by running GDB. And yep, we can just run a GDB, and then so this is basically I'm using this GDB server. So this program OpenOCD started a server on localhost on which I can connect, and then I'm connected in GDB, and then well, there is some program there that's running, but we know nothing about it. So let's build some program for it. Next. Okay, we'll skip this. Let's go directly to hardware because QEMU is not through. So they recommend to use some quick start stuff there with cargo generates. So cargo generates I didn't know, but we need to first install it. Normally it's already installed.
What does generate? What is cargo generate?
Yes, so cargo generate, I didn't know it, but it's basically a tool which fetch a project from GitHub and just create new stuff. So it's cool for this kind of tutorial.
So it creates like a skeleton kind of layout.
Exactly. Okay. So you give it a GitHub address. So this is the one from the. Right.
Yeah.
Sure. Okay, so I thought, what will I do with this? So I have a little screen, two little buttons. I thought I'd make a little snake game. So let's call it embedded snake. So it didn't like the underscore, but that's fine. Right. So there's some README that's kind of useful, but there's also all the information there. So it tells us, okay, first we need to edit this file. Config. We need to set the right target. So I'm having a Cortex M4, so I'm probably with floating point unit, so I'll just use this target. This is a bit tricky, so we also need to we need to tell the linker which memory address is it going to use, and so here so there I kind of find out the hard way by trying different address. Eventually I found like the default, no. So the default was 0, but it's the same as the one in the tutorial. And you can find this in the data sheet from the for the CPU, so the ARM thing. But so okay, and then we can try cargo build this thing. Go back here and actually. So this is basically the code which came with this tutorial. So it's basically it does nothing, right? It just do a loop. So the build is finished, good. So we will use this ARM GDB with the file that was generated. So that's this one. Okay, so the same localhost. So our thing is still running here in this other tab, this OpenSOCD, so we can still connect to this. We can load our program, and we can run it. So before running it, I'm going to put a breakpoint break at main. And now we can run it, continue, and there it is. So the breakpoint was reached. We can continue a bit. So nothing really happens, but so apparently there was an infinite loop there, but that's fine. That's basically what the program was doing. Okay, first step done. So it doesn't do much. What can we do with this? So we have a few buttons. There's a few LEDs. There's a screen. First, what every embedded developer does is to make a blinking LED. So how can we do that? That's a bit. Let's. How can we do that? Well, there is some. Yeah, we did that already. Okay. So I'm going to use those crates. It's a bit small again. So I'm going to use those crates. So those are some crates which will allow me to use this microcontroller without any unsafe code. We have here a STM32F4 crate, and those crates are actually kind of auto-generated from description file. So we can look at the documentation of it. Somehow I already visited all those links. So those crates are kind of auto-generated from some description files provided by the manufacturer of the CPU, and it has all it exposes all those addresses instead of like in embedded software you will just unsafe and then cast some numbers to some address, but it gives names to them. And there is one important. So there is different modules for different models, and basically the entry point is this peripherals data structures, which contains all of the peripherals. And the only safe way to get this peripheral is to call the take function, which returns an optional. So let's go back to our little program, and let's then use this. Let's peripheral equal. We need to. Yeah, actually, I just copy paste this. It's easier than typing everything, but so we're just gonna take this peripheral. So it's gonna return an option because only the first call to it will return something. And the second call will return none. So here's the first call on main, we can unwrap. But what this means is that there will be only one peripherals for the whole project. And if you need to pass a few peripherals to some subfunction, you can move them around. But so usually you would do that in your main function, and then all your subcomponents, they would acquire some of the peripherals. But what peripherals do we need? So then there is more. So this, where do I have this URL? There. So this is, so I Googled a bit more about this device, and I found the data sheet, which is kind of useful for doing development. And oh, behold. And so we have a few buttons, and so we see how those buttons are connected. So here, for example, we have one big LED, which it's a multicolored LED, but it's actually 3 LED, which are like for blue, red, and blue. And then there is a few more LEDs on the sides, which are then one by one. And what this datasheet is telling us is where the thing is connected. So if we zoom in, we see that the red LED, for example, is connected to PB4. So what does PB4 means? It's basically the port B4. And this corresponds to some GPIO. And so I also didn't know that. I just tried to find that out, and then by searching, I found that. So GPIO stands for General Purpose Input Output, and in our data structure here in peripherals, we have some of those GPIO. Yeah. So for example, the GPIO B. Strange. There should be stuff in it. What can we do? So this GPIOB basically is a structure which wraps a pointer, but you don't need to use that. There is strange. I don't see it in the documentation.
Are you the latest version?
Yeah. Yes, I'm It's the right one. I'm not the latest, which is because the other one doesn't work. But let's go back to our main program. And so this GPIO is then can be split into each individual component. So the red LED was connected to BP4. So we just ask for the BP4 thing, and I would really like to have the documentation of this. This is not good. Page is kind of big. So let's try the C one. It's all the same anyway. Right. Okay. But basically, when you have microcontrollers, basically a lot of things connected to those pins, and the pins, they can either be input or outputs, and even when they're inputs, they can be analog or digital, and you need to configure by setting some other values to some other registers to tell, no, this pin is going to be is meaning that. And the way to do that usually in C is that you just write some value to some register. You have to make sure it's the right value, and then you can use the pin as you can either read from it or write to it, to this register. But what does the Rust model, of course, is being safe, and it's in the type system. So unfortunately, this documentation is kind of not there. But maybe I need to search for. Well, but it's in the type system. So you say, okay, I want to configure this as a output pin in model push pull, and then it returns an pin which then you can set high or low. Or for example, if you have a button, the button which is connected to PA4 and PA10, then I'm configure them into input pin because they're buttons. And so again, the type system makes sure that you cannot misuse this, because the pin is configured as input or as output, and then you have the right thing. So no, you don't have weird stuff. What happens? Why I'm setting value in this register? It doesn't do anything. So here we have this program. So let's actually run it. Cargo build. So this program basically just I just assign some value to all the pins, and then I'm gonna set the blue LED to high. So I'm gonna turn it on and off. So it's building. I've seen that going faster. That's the demo effect. So I hope they did not just update that I created before. But
no.
let's try again. Oh. Did I not copy paste correctly? Maybe I didn't save. Okay. I didn't save all the thing. Okay, no, it's built, so I can run again. I will just type those commands here on the command line, so I don't have to type them every time. And yep, that's it. It's blinking. It's blinking blue. Okay, so what else do we have on this thing? We have like a little screen. So
I have a question.
Yes?
Does the type system actually prevent you? Can we try? Yes. Hey. Do I need to press something or no?
No.
Does the type system actually prevent you from making mistakes? For instance, what happens if you let the LED be an input and then try to set it to high?
Right, good question. So if I try to put LED be an input, then let's try to compile. No, so because the pin now is configured as input, so it doesn't have. You cannot set it. You can only read from it. So that's. I personally, I think this is makes it quite safe. It's a nice thing about Rust. Yes.
Can you change the type of pin at some point in your program, like turn an input into an output or something?
Yes, you can do that. So this into pin basically moves the pin to this thing. So you could first say that first you could have it as an input, do something with it, and and then, well, it will be another name. Well, I can reuse the name, but then I can put it back to so I can first set it as an input, do something with it, and then I can turn it back as an output. And it's a different type, so it's fine. So let's try to use this screen now. So I looked for the screen. What screen is this? It turns out that it's this component, and there's a crate for it. So let's just use this. Let's add that to the cargo, and let's again copy all this sample code. Okay, so the screen is connected with I2C, and I2C is a protocol to communicate between the CPU and the screen, and it basically just needs 2 pins. We can see that on this component. Where is it? The screen. That's this. And the screen basically is connected with the pin PB8 and PB9. And via I2C. So again, through our crates, here we can create an I2C device because it's kind of common, so they have abstraction for that, and we give them the PB8 and PB9 and a few other configuration. I just took the default stuff from the example from the screen driver. And then we can connect with I2C, and we get a graphics mode, and that comes from the embedded graphics crate. And this basically allows to do few drawing. I'll keep my loop here. So let's try. Okay, so there's few warnings, and yeah, so we have thankfully I have a webcam, so yeah, so here we have like our little, so first we have our LED is still blinking, and we have like a triangle. So we have, so that's what we draw. Basically we draw three lines to make a triangle. We draw a rectangle, and we draw a circle. So we have that in our thing. So that's basically what I need to, so that's basically what we need to get our more complex little game working. Then again, I'm gonna just copy paste this thing. So and you have to, I think my time is, how much time do I still have?
You're close to, but I think you're almost done, right?
Yes, right. I can just copy paste, and this, and there's more to copy paste. Yeah. Okay. So we build. Yep. And so now we have those two buttons. So I'm reading the input of this button, and I can pilot. It's really hard to do that. Wait, I will try to make it a bit bigger first. It's just, and when it takes a thing, and the screen is basically, it's a monochrome screen, but it has two colors, but it's like hard coded in the screen what are the colors. So, well, anyway, we can play with that. We can play with that later. So basically, what is this? Is basically just a loop. We look at the value of this button, this pin, if it's high or low. We check that we don't press two keys at the same time, and we kind of do that in a loop because we want to. I mean, a frame is a bit short to just press at the right moment. So I make it. I iterate 200 times. And I check 200 times whether one has press or not. And then I can just, it's just some basic, so the snake is basically just some data structure which has like, so it doesn't really use malloc or anything. It pre-allocates a list of points, and then it's going to draw them one by one. So that's basically, I just need to know where is my apple and where is my snake? Yeah. So, is there any questions? Then using the wireless size for later.
Questions? Yeah. Can we pass this? I can try. Yeah. Nice. Great.
Okay. My question is related to real-time operating systems.
Mm-hmm.
Do you know if there is anyone written in Rust for running this in embedded?
So I actually didn't research that. I would assume there is. So this is using. I don't remember if I mentioned this, but this is using no operating system whatsoever. So it's just running. So this is the operating system. So I have this little snake is the operating system.
So there is actually one. That guy who started writing the embedded book for him, he like 2 years ago started like proof of concept real-time operating system. I think it's called, the crate is called Cortex -M-RTFM real-time for the masses.
Okay.
So you can look at that. Yeah.
Great. Thank you.
Yeah. So there are also. Regarding the operating system, so there are some operating system in Rust, and you can also, of course, use any operating system and use your Rust code with it. But that's yeah. More questions? Well, if there is I actually have a.
Thank you.
I had a slides for the questions. So if you just want to download, I put it on GitHub, this little program, just if you just want to download it. But yeah.